Hi, my name is Ernest Perez, and with my group Alexander Estrella, Samuel Henderson, Joseph Touche, Sean Ryan, and Sam Sanders, advised by Dr. Rachmadian Wulandana and Dr. Damodaran Radhakrishnan, decided to design a self-balancing BallBot, STATERA, for our senior design project. To give you a better visual idea of what we're trying to accomplish in our project, displayed on screen is a video of the BallBot designed by Carnegie Mellon. A BallBot is a type of robot which implements a set of motors to maintain dynamic equilibrium on top of a ball, and uses this ball to translate about a space. The objective of this project was to design such a BallBot with reasonable production costs that is robust and low maintenance. Our main goal was to keep versatility in mind, such that STATERA would be useful to consumers in various environments. For example, the design's mobility may be used for something serious such as the transport of medical equipment, or a more mundane task like carrying groceries. Here, I'll pass it off to another member of our group, Samantha Sanders.
Purpose. STATERA was designed to explore the idea that a robot can fit into tighter spaces and still operate efficiently due to its unique means of mobility. An issue with robots that traverse via wheels is that they lack the maneuverability to move through obstacles with fluid motion. With the main mode of movement being the ball, STATERA can move on curves as opposed to straight lines of a four-wheeled robot. Engineering specifications. When building STATERA, we had no predetermined specifications for the project, so we had to come up with our own way to design this robot. We looked at other successful designs and took the best lessons from all of them. After some research, we determined that we needed to accomplish a few things. We needed to 1. Determine some degree limit that the robot could be away from center position to avoid toppling over. 2. It needed some kind of mobile power supply. 3. It needs to be robust, bumps, and glide on a smooth floor. And 4. Can navigate via sensors through any given environment.
Here, we will go into the engineering theory. The equations of motion were developed for STATERA, which approximates the motion of the BallBot, can be derived by developing a free body diagram of the system, and using energy methods to solve for them. Because STATERA is able to move in a three-dimensional space, the equations of motion are developed for 3 separate coordinates. The graphs on the right represent the displacement and acceleration of the BallBot as it continuously tilts towards a single direction. Displayed on screen is the interaction of electronic devices of STATERA. First, the Raspberry Pi collects the data from the gyroscope that is connected via the GPIO pins. Based on the angular data, the motor controller will determine the direction and speed of the stepper motors. The data collected from the gyroscope and the data pertaining to speed and direction are also logged to a database. In order to account for proximity and collision, sensors are installed on different parts of STATERA, and sends distance data to another database. This information is accessed by a server running on the Raspberry Pi, which then posts the most recent data to a locally hosted website. The BallBot STATERA underwent 3 design iterations that got it to its current state, with its final prototype seen on the left. Finite element analysis was done using simulation software such as ANSYS, SolidWorks, and MATLAB. This was to determine the structural and thermal properties of various materials that could withstand the weight of the components and the heat generated from them. Legs were developed to help stabilize movement and to prevent tipping over. Web interfacing components were enabled to display angular data and motor signal for monitoring purposes. For testing purposes, mock data was fed into the database and displayed on the graph in Figure 4. Figure 5 shows the signals being output to the motor in response to the signals it is receiving from the database given by the gyroscope. The total cost incurred to build a prototype was estimated to be around $240. Our allotted budget was $200, so we were about $40 over budget.
Future work. In future revisions, we would have liked to rebuild STATERA for a specific purpose. This particular iteration was built as a bare-bones system. The design is perfect to be outfitted according to user needs. We would have altered the design to change the shape, size, and or materials of the STATERA to make a more effective system. Lastly, we would have liked to fabricate the final prototype. All the theoretical knowledge we have gathered throughout the project would have been taken into account while building the system.
Thank you for viewing our presentation. We hope that we touched on a subject that piqued your interest and inspired some ideas in non-traditional robotic traversal. STATERA was a project that required all 3 engineering disciplines offered at SUNY New Paltz. To go from a concept design on a piece of paper to a fully simulated system capable of movement and balance using a few motors and a ball, we would like to thank both of our advisors on the project, Professor Rachmadian Wulandana and Professor Damodaran Radhakrishnan, for their hours of working with us to help us complete our goals set out at the beginning of this project.